My name is Mike Haney. I'm an ARPA-E program director. What we're doing with this session is giving you a series of short vignettes into our newest and latest ideas presented by our program directors and fellows. We certainly want to give you an understanding of what these ideas are, and they're in various stages of development, from recently approved program ideas to those that are still under internal review, to some that are even more nascent and embryonic, if you will. But in addition to giving you the ideas themselves, we want to give you an impression of what it takes to generate these ideas, how much we engage the community, how much we enjoy bringing different R&D communities together to tackle difficult problems. As I said, we're going to have 5 rapid-fire 8-minute presentations. No particular theme. However, for this session, you might discern a theme of energy efficiency, using energy efficiently, or maybe even avoiding the use of some energies altogether, which is kind of interesting. There is some logistics here. We're going, after the 5 8-minute presentations, we'll have a Q&A session for the entire panel. The instructions for texting the questions are there, and they will magically appear up here during the question and answer period for myself. So, without further ado, let me introduce the first speaker, Program Director Schiff.
This is a photograph of the famous glass house in Connecticut. The walls are large single panes of glass. It's a beautiful building, although I don't know how many of us here would actually want to live in it, as the architect did until he passed away a few years ago. Anyway, but as a longtime resident of Syracuse, New York, I can tell you that single pane windows like this come with their problems. As just one example, on a cold winter's night, if you have a sick kid, you might have the idea to put in a room humidifier to try to help out. And of course, what you'll discover is that the water condenses on the single pane windows and rolls off. And as an ARPA-E program director, I can tell you that 1/3 of all the windows in the United States are still single pane windows, even though they're much less efficient than contemporary windows. And just providing heat for those windows in winter uses 2% of the entire nation's energy supply. So ARPA-E is doing something about it. SHIELD is the name of our research program that we're in the midst of selecting for, that's going to develop low-cost technologies for transforming the single-pane windows into something better. Of course, they have to be better in their energy efficiency, but to actually sell them, they need to be better in other aspects, such as their comfort and their indoor air quality. So let's dig down a little deeper. A modern contemporary new construction will use a double pane window or an insulated glass unit. That's what IGU stands for. They're roughly 3 times more efficient as far as insulation goes than the traditional legacy single pane window. As I already mentioned, more than 1/3 of the windows in the United States remain single pane, and what might surprise you is that even in the relatively cold Northeast and Midwest, more than 1/4 of all the windows are still single pane. So that's certainly a problem for the nation's energy supply, but it's also an opportunity. So let's look at it more carefully. About $20 billion a year is spent by the owners of single pane windows to provide heat for those windows. We think that if the technology can be developed, the technology options can be developed properly, the savings on that will catalyze, they don't really completely pay for it, but will catalyze a retrofit market as large as $150 billion. The actual money at our disposal is larger than the heating bills for all the double pane and insulated glass units that currently exist. Okay, so that's what we want to do, is transform single pane windows to make them into something better. And as I mentioned, we're going to have to do something more than energy efficiency. So here's an example. The woman in the photo is sitting in a nice, bright office in Washington, D.C. Behind her is a large, very large single-pane window that gives great visibility, great light, but she's wearing a coat. And that's not because the air is cold in there. It's because that giant single-pane window radiatively cools her, and she needs to wear a coat. So one of the things that one has to tackle when one's tackling transforming single-pane windows is dealing with this secondary problem that's not directly related to energy efficiency. As another example, I'd already mentioned condensation. So condensation, of course, is somewhat unsightly, although sentimentally perhaps you like the look of that window. And somewhat unsightly if condensation rolls off, of course it does water damage. But perhaps most important of all is when you have single pane windows, in cold weather they set the relative humidity level in your house. If you find that it's condensation, it means you tried to raise it above a certain level that's set by the window itself and the exterior temperature. If it doesn't condense, it's actually even worse for indoor air quality because it means that your indoor relative humidity is well below the standards for indoor relative humidity for indoor air quality. As long as we're looking at wish lists, let's look at soundproofing. A driver for window improvement in many places, especially cities, is soundproofing. People will upgrade their windows to try and reduce the noise from passing ambulances at night. Interestingly, this is a case where the traditional single-pane window is only marginally worse than a more modern IGU or double-pane window. This is an area of technology that clearly needs development. And finally, we are ARPA-E. These windows, the single-pane windows, are, if you like, the grunting energy hogs of the building envelope, and we'd like to do something about it. Okay, so SHIELD is the name of the research program that ARPA-E is in the midst of starting right now. Concept papers were already due last fall, so that section is over with. Full applications were invited recently, and we expect to be starting award negotiations in a few months. There are actually two SHIELD programs. There's up to $10 million for small businesses and $20 million essentially for everyone else, including small businesses. All right, well, SHIELD has three categories of research project that it's going to fund. The targets in all cases are required to be condensation resistance, radiative comfort, and insulation. There's also an option for additional qualities that you can propose that could be proposed by the applicants, but those are the mandatory ones. There will be three research categories. One is something you could stick on to an existing pane to improve it. Currently, window films are an example of that kind of technology, though they wouldn't meet the targets of this program with just a simple window film. Second, you can develop an improved pane that can be slotted in to the existing window frame or sash. And then finally, there's an option for innovative technologies that are required to drive 1 and 2. It's very difficult to achieve those first two category targets today, the existing pane or the improved pane, without new technologies. So this is a chance to develop the technologies in the service of that. As two examples, super insulating but also super transparent materials that could be applied to a window perhaps as a spray paint really don't exist today, although there's some good ideas for how that might be done. As another example, emissivity control, I mentioned radiative comfort, is something that needs to be part of the solution most likely, and improvements are needed there to really achieve all the targets. So those are the examples. So I don't actually want to drill too much, I don't want to drill any further into the research targets. What I'd like to take my last couple of minutes to do is to explain that all ARPA-E research projects come with the second half. You know, if it works, will it matter? So this has to do with will it matter. So each project in an ARPA-E portfolio explores commercialization, is expected to develop intellectual property and to explore the market along with the technical work. So in addition to myself, Graciela Blanchet is a technology to market advisor with a very distinguished prior career. And her job is to help manage and facilitate this aspect of all of the awards in SHIELD. All of our programs have technology to market advisors. Just as an example of the kinds of activities where, depending on what line of work you're in, you might be participating, awardees start seeking industry advisors. That's quite important, especially for a relatively applied program. Licensees of their technology, of course, follow-on investors and partners. And we try to facilitate that, and Graciela is the member of the team who gets principal responsibility for that. If you're interested in that, Graciela is around, as am I, and we can explain broadly, nothing specific to SHIELD, about how that works. All right, so architects, of course, know that single-pane windows look great, and Philip Johnson, the architect of this building, lived there until he died. We can now envision transforming those single-pane windows so that they become beautiful not only to the architect, but to the homeowner and the engineer. And finally, we certainly hope they will also be interesting as business and investment opportunities to the general buildings community. Thanks for your time. And I'd like to introduce the next speaker is Jennifer Gerbi, Program Director at ARPA-E.
Thank you, Eric. I would like us to all use less energy without even noticing. The without even noticing part is really, really hard. We live in a really smart age. We have computers on us that have sensors in them and walk around all the time. And yet, the way we heat and cool and ventilate our buildings doesn't really make use of any of that information. I'd really like to change that. As a new program director at ARPA-E, I get to develop with some very, very smart and amazing people at the agency a new program. It is a ton of fun, and this is talking about the program that I'd like to start. It is in the stage where I want your input. I don't care if you're an end user, an inventor, an investor, a utility, anybody in this space. If you have something to say, I would love to hear it. Please come find me. Why? Just for 2 seconds, we use too much energy. We all know that. That's why we're all here. If we can target 1% of that usage, which is what we would call 1 quad, that would be a really big deal. So I want to give you an idea of the scale of the amount of energy that we use to heat, cool, and ventilate our buildings. 40% of all the energy we use is in buildings, and you heard that statistic today in one of the keynote talks. Half of that goes to heating and cooling and ventilating. That's a huge number. That number is way too big, because if you think about your own personal situation, there are probably times you don't need to heat or cool the space that you're in as much because you're not in it anymore. So residential, commercial, they each use about the same amount of energy. If we can reduce usage, that reduces impact by 2 times that, because we waste half of the energy just in producing the energy. If we reduce our HVAC usage by 2.5%, that's an entire quad of energy. So this is why this is so exciting to me, because this could have a very, very big impact with a very small change in usage of HVAC. Now, this is not a new problem. I'm not the first person that ever thought about this. So what if we had some sort of technology? What if we had an electronic butler, and when we weren't home, that butler could turn the heat down for us or turn the AC off for us? What if we had this? Well, I don't know about you, but I was in a house with 2 PhDs, and this was never set right. Now, maybe we were lazy. We definitely were lazy, but is it just us? I don't know. Our solution in Michigan was to set it to 60 degrees in the winter and just leave it that way all the time. I guarantee you will notice that if you do that. Your cats get really big. It's a whole mess. So can we do this better? Well, why doesn't this work? This is actually really interesting, and it's not just us. This doesn't work for most people who try to use it. And I don't think 90% of people are lazy. I think that there's a really subtle interaction with that tech-to-human interface. And actually, there's a panel tomorrow at 4 that's going to talk all about this with some of the key people in this field. So my idea is, let's get rid of that entirely. Let's not even need an interface. You can have one if you want, but what can we do that doesn't require us as humans to take an active involvement in changing those numbers? And if you want to extend it to commercial use, this gets really complicated. Now you add ventilation, you have multiple zones, very big systems that need to be balanced. You're not just home or not home. You might have 3 people, you might have 2,000 people. This gets really complicated. But if you had this magic information of knowing where people are and how many people are in there, now you can start to use your HVAC smarter and save energy. So what you need is occupancy sensing. And you've probably heard this. There are people working on this. But it is really hard to do. It's not motion sensing. It's not when you walk in your office and the lights turn on, or you wave your arms frantically because they turned off again. This is really, truly knowing where a human body is in a space. Not who it is, but just where it is and how many there are. So if you have a commercial building that looks like this with 3 people, or you have a building that looks like this, you're going to run your HVAC very, very differently. And we can really start to save some energy if we do that. If we had this info, so P&L did a study on this and did a very in-depth simulation looking at large office buildings. And 80% of these buildings already have HVAC fans that have variable speed control, which is what can save a lot of the energy. And if they just knew this occupancy information, you could save 15% of your energy from HVAC. And even in the most challenging of climates, Miami, you still save over 5. That's huge to me. That's saying, look, if we only had this information, we could use it, and we could actually use it right now. There's a relatively low technical barrier to entry for this, and it's also a huge market. So that's very exciting on both those counts. But what do we need to make this work? Well, If you were DARPA and you had millions and millions of dollars, you could outfit the building to not just know where people are and how many they are, but you would know who they are, which maybe you don't want to know. And you could do it for a very large amount of money. But people do not have a large amount of money to retrofit their buildings to save with HVAC costs. So that cost is what's going to drive this technology to be a fundamentally different kind of technology than what we've been trying to use. Also, you need the right functionality, and that's a real challenge to try to get a true occupancy sensor to work. I really like the example of the little Amazon Dash button that everybody thought was sort of an April Fool's joke. I have one right here. It connects to your Wi-Fi, and it orders detergent for you, and it has a radio in here, and most of this is the AAA battery. So as electronics become more low power and start to become more consolidated, the price goes down. So how can we integrate occupancy sensors into this, or any other sensors that we need in terms of air quality? Maybe we need CO2 sensors, or we need some other sensors. How can we be smart about this? How can we make it super cheap so that people can make money selling these and the services, people can afford to buy them, and we can impact our energy usage? Sorry. So when we think about what our options are in this space, again, people have been looking here. There's definite proof of market interest in this space. We think about image processing and trying to do sort of low power effective image processing, but there's other ways you can do this. What if you use a special algorithm with audio signals? What if you use some sort of radio wavelength attenuation? What if you couple one of these with counting what MAC addresses are on your Wi-Fi servers? I mean, there's many different ways you can think of doing this. I think the key is to think about what type of building you're trying to save energy in, what the usage of people are in that building, and what sensor makes the most sense to use. And all of this, to me, is in scope, for this program. I'm not trying to say what the answer is. What we're trying to do is to say, here's what the metrics need to be, here's what the cost needs to be, here's really what we need to achieve to save energy. You guys are the smart ones that are going to figure out how to do this. We're going to pay for it, but we're not going to solve this problem. You're going to solve this problem. Okay. So again, I just want to emphasize that I want your input. I don't care who you are in this chain. This will only be successful if we can get everybody together from the inventor all the way to the end user to understand what will work. I'm going to be in Chesapeake Bay tomorrow from 5:30 to 6:30. If anybody can't catch me, come catch me then, and we'll chat about this more. And I really look forward to getting your input. Thank you very much. Next is Jason Rugolo, a program director at ARPA-E.
Thanks, John. Everyone, welcome to the summit. Thank you. This is Jason Rugolo. I'm an ARPA-E program director, and I'm going to talk to you about advanced telepresence technologies to reduce passenger transportation. Here's a picture of the big, beautiful building we're in. Eric and Jenny told us about how terrible they are with big windows and HVAC that's not controlled properly. I just got a quick question for everybody. Show of hands. How many people live in the Gaylord Center? Okay. Oh, you do? That's not good. I'm kidding. None of us live here, but we all had to get here somehow. So a real show of hands. How many people took one of these to get here? Wow. That's pretty much everybody. Most people. Okay, keep your hand up if you came from the West Coast. Let's say Denver and West. Wow. So like more than half of that 8-hour round trip that you took is worth about 4 months of energy consumption. Okay, so you do it 3 times in a year and you double the typical person's energy consumption. I think most of us are probably guilty of that. So it's a 4,000 kilowatt hour round trip. Total travel, total passenger transportation is about 2 quads per year. Okay, again, we do 100 quads per year as a country, so it's 2%. And these all the time, right? Cars and trucks. Cars have about 7 quads a year. Footprint. Trucks have about 8 quads a year. Right, you add it all together and add another quad or so in other passenger transportation, you get 18 quads per year in moving people around. Okay. So I want to ask the question, why? Okay. Why are we scurrying around the surface of this big, beautiful marble in space? Why do we do that, right? Now, we could be here all day trying to answer that question, so I'll be more specific. Why did the vast majority of you fly here to the ARPA-E Summit? You might say, well, I had to get here somehow, right? But that's not what I mean. I mean more deeply, why are we all sitting in this poorly lit room in uncomfortable chairs, watching and listening to my colleagues and I talk about energy? Right? Well, watching and listening are the operative words there. Fundamentally, we move from A to B, all transportation, all 18 quads, is to get these 6 things here, right, in this room. It's our on the left, the eyes, ears, nose, mouth, and dermis, and our processor on the right, right? All that sensory information goes into our brain, and we create a perception of presence. Now, we know that we have telepresence technologies, and so that's that I find interesting. Technology have to say, is this me? Is this really annoying for everybody? Is there a problem? It's really annoying for Cheryl? Okay. All right, well, I'll keep going and try to stop being Italian and my arms. So what does technology have to say? Right? It's advanced technologies that have gotten us into this mess, right? This 18 quad per year mess. Thanks, Ben. And I think it's advanced technologies that are going to get us out of it, right? Planes, trains, and automobiles transformed the entire economy, but also came along with an 18 quad per year energy footprint, and that's not going down, right? So I think advanced technologies will take us out of this. Here are just some recent advanced technologies related to our sensory inputs. So we have eye-related developments, ear-related developments, touch-related developments, camera sensors, high-resolution screens, projector technologies. We're all familiar with these things in consumer electronics. Right? Microphones, speakers, haptic feedback is coming into its own. Of course, we've seen massive computational power for cheap over the last, say, 20, 30 years. High bandwidth internet everywhere over the last, say, 10 to 15 years. Game and movie rendering has just leaps and bounds of progress. Physics engines have gotten a lot better. And of course, we see a consumer adoption of virtual interaction. So people now cultivate online personas in social media. These have culminated in kind of this new latest fad, billions of dollars going into head-mounted displays. And people talk about a future where we're all interacting in virtual environments. Now, let's take a quick step back. You can't flip a hamburger with a head-mounted display, right? So we did an analysis to try to break down passenger transportation into the various objectives, right? The reasons for which we travel. So we found 3. So communication, labor, and experience, right? So communication is the reason we're all here today. It's to convey or consume information, right? Labor is to physically affect the environment around you. So this is flipping hamburgers or driving to a factory in order to screw in screws on an assembly line. And experience is tautologically defined as predominantly to experience. We don't want to touch that category, right? So this is going to the beach or going to church, and we're not interested. But we found there's about 8 quads in communication, 5 quads in labor, and then another 5 in experience that we're not going to touch. So I think advanced technologies, advanced telepresence technologies can hit these 13 quads. Mike Kane, who's a fellow, is going to talk about labor, and I'm going to focus the rest of the talk on the 8 quads in communication. So fundamentally, I believe that someday we'll only travel when we want to, right? That 5 quads in experience. And the reason that we don't today for communication is because present-day communication solutions lack all of these things. So I'm not going to run through them all, but this is just a short list, right? Simultaneity, like, you know, latency in Skype communication is terrible. It's hard to have a conversation. Eye contact, immersion is bad, right? You have flattering light and, issues, and angles are bad. And so people just aren't comfortable communicating at a distance with those things. And of course, we all couldn't meet in a room like this via Skype. If anyone's tried to have a conference in Hangouts or Skype with more than 5 people, you know what I'm talking about. How many people in the room have heard of Second Life? It's actually fewer than I thought. Okay, let's say maybe a fifth of us or something. So Second Life is an online digital community, right? It's not really a game, but it's kind of like a game. You get in and you're a virtual avatar, and you go around and you interact with people, right? Why aren't we all having this conference in Second Life? Why did we send 2,000 people from around the country to this one spot in DC? Well, it's because in Second Life, you're an avatar, and you're either this cute red fuzzy thing, or you're this, which is a very creepy computer graphics version of yourself. Right? This is called the uncanny valley. As you try to make it more and more real, the digital representation of a person, it gets worse and worse until you're perfect, and then, you know, presumably we could all meet in a digital space. So we've been getting much closer to perfect. So this is some of Paul Debevic's recent work. He's taking a 3D photo of the president, our fearless leader. Now, this contraption, it takes a minute or so to build this avatar. It takes hundreds of pictures from all different angles and lighting conditions. It takes different polarizations, and then it gets the skin reflectance, right? So it's very, very detailed, and you end up with something like this, right? Now, if you go online, you'll be able to search this in 3D, and you'll see kind of how good it is. But I mean, from here, it almost looks like a photograph, right? This is very, very good. So I would say this passes the uncanny valley test. If we could be digital avatars in a virtual world and look like this, that would be great. Unfortunately, the moment that you try to animate it, right, make it move like a person, it gets creepy again, right? So that I see as the research challenge, right, is how do we make a digital avatar act and feel like humans, okay? And so I'm proposing something like a digital avatar Turing test. Two video booths, and one, you have an A/B switch, and you have a video feed between them, and then you switch it to the digital avatar version, right? And the moment you can't tell the difference between the avatar and the video feed is the moment that we've kind of been able to represent ourselves digitally, and conceivably could get rid of buildings like this, which are a quad a year, and replace that with virtual communities. So thank you, that's me. I'm gonna introduce Mike Kane here. He's a fellow at ARPA-E, and he's going to talk about Tele-Robotics for the same purposes.
Thank you, Jason. Yeah, so as Jason just introduced, telepresence opportunities to reduce unnecessary travel and to save energy. But sometimes you want to be present somewhere, but you also want to engage in that physical world. You want to manipulate something, you want to turn a wrench, you want to flip a burger. So I'd like to investigate a little more about what opportunities or how we might be able to achieve those same energy savings where we have to engage with that physical world. So how much energy does the US workforce consume that's doing labor? They leave their house empty at home. They travel 2 hours a week back and forth to work. There's lighting and air conditioning on in the workplace to make a safe and comfortable environment. That all adds up to about 5% of all US energy consumption. Some people have postulated robots to the rescue, that robots will solve all the world's problems. But all plausible roadmaps for automation have serious limitations. In terms of perceiving complex environments, whether it's a cluttered environment of being able to separate and understand different objects, or if objects are soft or irregularly shaped, automation systems have an extremely difficult time and will likely continue to do so. Making decisions in those complex environments or in environments where it's the first time that you've identified something. Maybe you've learned intuition since you were a young toddler going around experimenting with things. Can we provide that same full life experience intuition to an automated system? Maybe, but it's unlikely. And then if we're looking at augmenting our healthcare workforce, we need to have that natural human touch. So ARPA-E is interested in kind of a balance between these two. Can we let people do what they're good at, and can we let robots do what they're good at? And so can we have a telepresence or a teleoperated system where we have people working at home, operating robotic systems in the factory or in the field? Or we've actually identified 4 major areas that are ripe for transformation. The first one is a remote service call. So this is a plumber or an expert coming out to a site, and they might only come out to that one site once a year or even less. So it's important that the costs remain low. And there's a reason that doctors don't make house calls anymore, and that's because traveling to and from your house is just not a valuable use of the doctor's time. So can we make tele-robotic systems that make better use of these experts' time? When we have experts that are on site more and more often, maybe an at-home chef or a monitor in a nuclear waste site. So completely different types of jobs, but an expert in residence. If we want to achieve that of affordable, timely help when we need it, that expert needs to have a high sense of presence in that environment because it's likely going to be constantly changing, and they probably will need some sense of dexterity for fine manipulation tasks. The third major area is a remote desktop for factory workers. So this is kind of what I talked about before, where automated robotics might fail in certain situations, but the teleoperator can help fill in those automated gaps. that sharing of autonomy between a person and a robotic system, especially over a lossy internet link, is still an open problem in the research community. And then the last major area is kind of a little bit more out there, but how many times have you gone to buy something online and you wanted to feel how heavy it was or how flexible it was or what the texture was? If we could create robotic systems that had incredible sensing and feedback, we could dramatically improve the shopping experience and continue to augment the energy savings that we have through online shopping. What barriers do we have to overcome in order to realize these types of systems? Are they as complicated to control as a nuclear reactor, or is they as simple as an iPad and a toddler? Figures it out right away. A robot can easily identify a bolt and turn it if it's on a flat plate, but if that bolt is hidden underneath something or around a corner, the human intuition might be able to achieve that. Or once again, if we have like boutique products, the first time we're designing something or manufacturing something, that human intuition through teleoperation might actually be a great opportunity here. But that human has to be able to feel present so that intuition is activated. If we're trying to maintain costs low, we should use tools that already exist, so we should have dexterous manipulators that almost simulate a human hand. But if we want that type of dexterity, that type of ease of use, that presence, costs need to be extremely low. Current industrial robotic systems cost as much as a house. There's products that are just starting to come to the market now where you can get almost human-like arms for about the price of a car. But if we want these in every household, they need to cost as much as a refrigerator or any other household appliance. We've identified two major research opportunities here, the first being low-cost actuation. So if anyone out in the audience, I'm really interested in hearing back from you. If you have ideas for entirely new, novel mechanisms that scale incredibly well at ultra-low cost, whether these might be electrochemical actuators or pneumatic actuation technologies. If we use more traditional gears, can we, instead of using highly precise machined gears, can we use low-cost parts and improve the performance with closed-loop control? And then lastly, for those in the audience into manufacturing, are there integrated manufacturing processes where we can integrate the electro and the mechanical parts of an electromechanical actuator to dramatically reduce the costs? Because the actuation parts are a third or more of the actual cost of the robotic system. And the last major research opportunity is for controls and a user interface or user experience. Because we're going to be controlling these devices remotely over an internet link, we might have to lose packets, or we might have to buffer as if we buffer online streaming video. But in order to do that with a physical environment, we almost need to be predictive. So can the robotic system or the remote system understand the user's intentions? If there's two objects in the workplace, can the remote system identify which one of those objects the person wants to move towards? And then if a packet is lost, the robotic system can move towards the one that was intended to without the user having to explicitly express their intent. If we want to maintain costs low, but we also want a sense of presence in that environment, we have to create systems that are natural and easy to use, but also, once again, low cost, both on the sensing in the remote environment and sensing the user's intentions. If we can create ultra low cost, natural, easy to use systems, we can improve quality of life for these workers and dramatically reduce our energy consumption. So I'm really interested in continuing the conversation with you as we continue to develop this program with Jason. Next, I'd like to introduce Program Director Mike Haney. Thanks.
Well, in case you haven't noticed, data centers have been proliferating like rabbits, like big energy-hungry rabbits. The photo on the left is a typical photo of a mega-scale, warehouse-scale data center, this one from Facebook. But the fact is, most of the energy consumed in data centers is by smaller data centers, smaller scale ones. What data centers at all scales have in common is that they are networks of computing elements, like shown in the middle picture, of a server board. As this technology, the server and other computational technologies advance, it's putting more and more of a load on the network itself, making it very hard, much more hard for it to keep up in an energy efficient sense. In fact, we're driving the energy efficiency issue all the way down to the chip where the metal interconnects are running out of steam. Hence, we are asking the question that is the title of this talk. And we think that in the future, integrated photonics may be a solution to overcome this barrier. Before we get into that, let's talk a bit about the problem itself. Information and communications technology, ICT, is the fastest growing sector in energy consumption. There are a lot of ways of just defining that. Our keynote speaker this morning mentioned 50 billion devices connected to the internet by the year 2020. That's a lot. Here's another measure. The global data center traffic is projected to be 100 zettabytes by 2020. Raise your hand if you know what a zettabyte is. Is that all? I'll give you a hint. It's 1,000 exabits. Does that help? Anyway, it's a lot of bits. It's 10 to the 21 bits per year. So 100 of those, 10 to the 23 bits per year between data centers. Again, a big number, hard to get your head around that. So we want to boil it down into something we can. That's equivalent to 200 million selfies per second. If we want to, you could use cat videos or another equivalent metric if you like. So that's a lot. They take a lot of energy, but just keep in mind they are not merely data warehouses, even though there's a lot of data, of course. But they are really more properly termed data processing centers. There's a lot of computation going on. Every bit that comes into or out of a data center results in many, many more bits traversing inside the data center, using a lot of energy. How much? Well, currently, data centers in the US use about 12 gigawatts, or 2.5% of the grid load. That's a lot, but what's more concerning is that this is growing exponentially, perhaps even getting worse in the out years. This is not a tenable situation, and we need to address this situation. So we need to make data centers more efficient. Here's a schematic diagram of a data center showing the network inside the yellow box. It's connected to the grid through some electrical power conditioning equipment. There's cooling required. There's many opportunities to improve the efficiency of data centers. But perhaps the best opportunity for transformative impact is through the network architecture itself. If we can overcome the bandwidth limits to chips that are appearing, then we can enable whole new network topologies and thereby provide a multiplicative performance enhancement. On the right there is a schematic of a typical data center network called a fat tree. Perhaps we can affect that topology itself and have a major impact. Well, why do we think optics is a possible solution? Well, optics is already a solution in data centers. You may be aware that those many, many racks connected in data centers are connected through fiber optics. That overcame a bottleneck, a brick wall that came about because of coaxial copper cable. Emerging very shortly, we're going to bring optics closer inside the rack to the drawer. And in the not too distant future, with this so-called system disaggregation or subsystem aggregation, if you will, optics will come to the board. And this is already on the drawing board. However, we'd like to get to the next step out in the out years to this sort of fatter and flatter networks and transform the way we do data centers. But that will be only enabled by lower energy per bit to the chips and higher bandwidth density overall in the network architecture. Well, there's a brick wall, and that brick wall is the metal interconnects. Let's talk a little bit about that brick wall. Here's a photo of a typical chip package with all the metal dots connected to metal wires in the board. Fundamentally, if you need to go from point A to point B, it's going to take you greater than a picojoule per bit on a metal trace. More important, the density of those metal traces is going to be limited, and the density of the bandwidth on that metal trace is going to be limited to less than 100 gigabits per second per wire. To overcome that brick wall, we can think about photonic interconnects using optical waves, in which now at the interchip level, we can get much less than a picojoule per bit. This has been shown in the laboratory, and much greater than 100 gigabits per second on individual waveguides. So the opportunity here is to overcome the metal trace input-output limit in future servers and increase network throughput. Well, how might that manifest? Well, here's another example of that fat tree interconnection fabric. If we had very dense optical interconnects at the switch nodes, we might convert that topology into something that looks like this. This is just one example of a shorter tree, fewer store and forward steps, much more energy efficient potentially. So that brick wall we talked about, we think can be eliminated by bringing optics in an integrated form all the way to the chip carrier, sort of that last brick wall. And the opportunity here is to use integrated photonic interconnects to overcome that brick wall, as opposed to discrete photonics, which would be to the left of that former brick wall. So if we go look at the technology space, it's a very rich technology space option. I won't have time to go into the details, but there are many technology platforms for links, microlasers called VCSELs, silicon photonics technology. There are also integrated photonic switch technologies. I think the opportunity here is to, in a multidisciplinary fashion, combine those technologies with network architecture. And now we can re-architect those data centers to take advantage of these technology platforms. So let's go back to this chart. We in the government like to talk in terms of white space charts to help us define the challenge and opportunity space. If you look at this chart, clearly we want to be to the right and down. That's where we'd like to be. And so we'd like to get, well, instead of white space, we'll call it green space, because we're ARPA-E. So we want to drive that curve down and to the right. To do that, we think we can do that with photonic input and output at less than a picojoule per bit and achieving low latency switch fabrics. We are in the midst of putting together a funding opportunity, which will be published very shortly. In fact, there is a pre-publication to that funding opportunity announcement called a Teaming Partner List, just been published. We have a title for that. It's a bit of a mouthful, so I'll read it to you. Energy efficient, lightwave, integrated technology enabling networks that enhance data centers. Very descriptive, but a bit of a mouthful. So we like its shortened version better, enlightened. I hope you agree it's a bit inspired as an acronym. So I'm looking forward to learning about your ideas about how to improve efficiency in data centers. And we will now move on to the Q&A session. Thank you very much. Speaking of data centers, oops, I think I just lost it. Which app is it on here? Or which app it was for the Q&A? Was it under messages? No. I accidentally closed the app, folks, so I need to... How do you do that? Swipe over? Adam, come up here for a second. On Safari. Perfect. All right, thanks. Okay, good. So we'll have some questions now, and we'll take as many questions as we can. And of course, you can find us if during the conference if we don't have your question answered here. So here's a question for Jason. Could advanced telepresence technology handle informal side conversations in networking, such as, and I didn't get the last part of that.
I think I get the question. So the answer is yes. The only way that I have seen that you could do that is by communicating in a virtual environment. You can imagine any number of virtual interfaces, whether it be a monitor on your desk, where you're kind of like, navigating through a space, or you could be immersed in a head-mounted display or something like that. But we could literally, I've seen these things. I know it's hard to describe. We could literally all be in a room right now as bad avatars, and we could all stand out in the hallway and talk. Right now, that technology exists. And I think the reason we're not is because, we'd all be cartoons and look kind of creepy to each other, or big fuzzies if that's kind of the way you are. But so I think the answer is yes. It's just, there are still things that are necessary. One big challenge is bandwidth. So we need to keep the bandwidth way down if we're going to have 400 people meeting at the same time.
Very good. There are no questions appearing on my tablet.
Was I the only one who got a question?
Brian, are you sending some more questions my way? We can try this the old-fashioned way. Let's do that while we're waiting. Someone, I saw a hand over here. Another question? Stand up, please. Speak very loudly. A question for Jenny about, did you hear the question?
Thank you. I'll repeat the question. The question was, how would this program, this proposed program, be better than demand-controlled ventilation, which is already in some buildings now? It would be better, but yes, that's part of what this needs to do. So if you have better data, you can do a better job at that. I was positive somebody was going to ask me, isn't Nest already doing this? So I'm also going to answer that question. And the question, to answer to me, is that this is a huge market, and there is absolutely a place for the Mercedes of thermostats. And to me, Nest is the Mercedes of thermostats. It's $250. It's beautiful, but it's not going to be in everybody's home. We need something for the 80% of people that are not going to buy a Mercedes. We need $10 thermostats that you never have to touch. But that's a very good question, and I think whatever this program does in terms of have data that we don't have now, you have to be able to integrate it into current systems to make them work better. And different systems work in different ways. And so part of this program is to understand that and to target where we can make the biggest impact.
Very good. We're back online here. So the next question's for Mike. If remote control of robots successfully becomes widespread, will today's network security be sufficient?
Yeah, that's definitely an issue in dealing with the security, and every time you create a new internet point or internet access point into a system, you create a vector for attack. So there's definitely opportunities for securing the communication between these points. It's definitely something we can't ignore, but I think it's a problem that can be solved.
Okay, thank you. Another question for Jason. What would be required for mass adoption? What's the roadmap for commercialization?
This is an excellent question. I think if you knew the answer, you'd be a billionaire right now. I think that, what we're trying to do is prioritize all the various aspects of presence, right? And in order to do this, we've engaged anthropologists and sociologists, right? Not typical scientists, just to say, how important is making eye contact with somebody? How important is interpersonal distance? How important is, hand gestures and all that kind of stuff? And so I think, what I proposed is a bit of a cop-out, right? This Turing test is when avatars are perfect and 100% can replace a human, and then the answer is, well, you could get mass adoption because you can't tell the difference, right? But I think a much harder question, and something I've been engaged in, is how good is good enough, right? As we move along towards, past the uncanny valley and further towards being able to make more perfect digital representations, when do we get that huge uptrend in adoption and this massive plummeting of transportation technology that we hope for? I think it's an open question.
Thank you. Another question for Jenny. Are building owners going to be willing to pay for this?
That is an excellent question. I think that's one of the biggest problems is how much would the cost of one of these systems be? And there's been a lot of promises made in the past. There's been building retrofits, and then the promised savings was not seen because these are very complex systems. So I think we have to take that very seriously. We have to engage those end users and truly understand how much these systems have to cost installed. That's a big, big point. And what does that return on investment need to be? And I think we need to target something that's extremely attractive. And then part of this also needs to be showing proof that this actually can work as promised. So I think that's a very good question, and I think cost is a huge part of this.
Thank you. This is a question about data centers. For me, the tech base for integrated photonics is rich, but what has been the barrier to acceptance thus far, especially in datacom? Is it cost, and how should we address this? This is an excellent question. I think the barrier to insertion of integrated photonics so far has probably been related to the lack of an application domain. The silicon and metal interconnect folks are very clever and have so far been able to tackle the performance challenges quite well. But I think what is needed, what will be needed, is a large opportunity, meaning economies of scale needs to push or pull photonics into the cost-effective deployment with mass fabrication techniques. I will also mention that we can relate this to the President's NMI initiative, manufacturing initiatives. There's a new one in photonics aimed just at this, for photonics. What we'd like to do at ARPA-E is give them something to build, and data centers is a good opportunity to motivate that. Let's see. Another HVAC question. HVAC startups have historically had a relatively short path to revenue. And let's see here. I can't read the whole sentence here. HVAC startups have historically had a short path to revenue. What do you see ARPA-E's role in this space?
Another really good question. I think it's interesting because it seems like this is something that would be closer to commercialization maybe than something that we would normally work on. But I think the path that a lot of people are on is using a certain kind of technology, and once you're on that path, it's really hard to break out of it. ARPA-E's role here is to actually be able to back up, look at new technology, new ways of sensing, maybe developing new sensors and sensing materials to put us on a fundamentally different path. And I'm hoping that that path is much, much cheaper than the other path and also works better and gives us data we didn't have before. So to me, ARPA-E, it enables even people currently in this space to have access to technology that's going to be fundamentally different than what they're using today so that they can have a much bigger impact much more cheaply.
Thank you. This is a question, I think, for Jenny, but maybe Eric will have a comment too. Do you envision a program on building envelopes in the near future?
Well, of course, SHIELD is a program on building envelopes. I would envision that ARPA-E will continue to find opportunities in the building envelope and the general building space, but it's determined to some extent by the particular program directors we hire and by our perception of the opportunity for a program typical of ARPA-E, which is about a $30 million footprint.
Okay. Another question for Eric. Is, quote, radiative comfort equivalent to thermal insulation?
No. Oh, would you like more? There is a relationship. If you're uncomfortable radiatively, that component of the insulation that's associated with radiation is poor. So you can have radiative comfort in a window that's actually fairly poor performing thermally. So the answer is yes and no.
Okay. And the second part of that question has to do with, they said 3M has developed some mature film products. I guess you may be aware of that.
I was, without mentioning, there's several manufacturers of excellent window films. They all actually give you excellent radiative comfort, but actually deteriorate condensation performance and the improvements to the actual U factor, which is the usual thing that you use to characterize insulation, is good but not great.
Okay, question for Jason. Will people actually travel more with advanced telepresence and consequently have more free time?
Okay, well, I'll spin that question a little bit. So as you create more, better telepresence, you're going to create more connections over distance, right? You can imagine interacting with many more people in Europe than you do now because it doesn't cost a plane flight to get there to do a handshake on a business deal, right? So I think the answer is maybe. All we can go on is what we've seen in the past, right? Which is that telecommunications has kind of co-evolved with a massive increase in passenger miles traveled. I also believe that there is a saturation point, right? With globalization, we have already connected many people across the entire globe. The population is going to stop growing. And I think eventually, kind of the connections that we create will saturate out. And ultimately, what we want is to get more, higher efficiency from these connections that we make. So right now, each connection takes, if you want to fly to China, it's something 15,000 kilowatt hours or something like that, right? And if you just, get immersed in a digital reality where there's a Chinese person that you want to talk to, then it takes something like 15 watts, right? And so if passenger miles traveled increases a little bit in the near term with better telecommunications technology, I think that's okay, because it's the general trajectory we're following right now. Eventually, as we get closer to perfect, I think that we're going to travel only when we want to for those more experience-based cases.
Thank you. I have two different HVAC questions. People are interested in HVAC. So one question is, what about privacy? And the second question is, what about monitoring HVAC equipment, like detecting refrigerant leaks?
So the first question, I think, what about privacy, is a really important question, because I think people, and rightfully so, get spooked about this. So I think that would be part of what would make a technology more attractive, is if it is inherently private. So if you are using a somewhat passive way of detecting whether there are bags of water in the area, which is what we all are, and you can just count that number of bags of water, you never know who that bag of water was. But if you use an image processing technology, then you have to say, well, look, the resolution is so low you couldn't possibly tell who that is. People might not believe that. So that is an important issue, and part of what would, again, make it beneficial is if you say this is inherently private and here's why. So some technologies are like that, some are a little bit less like that. So I think that that's an important question. I mean, to move that towards something else also is actually the security of our HVAC systems. HVAC systems are ridiculously unsecure when you think about how much damage that they could wreak. So if you think about having these advanced sensor technologies, they could also make the entire system more secure, which is something that we really need. Okay. The other question was about actually
about
sensing,
detecting leaks and things like that.
So that's actually not, I would say that that's not in the scope of this program.
Okay, thanks. We'll have one more question for, let's see here, Jason. Where do you think teleoperation will make its first appearance? And it's cut off here, but I think it says beyond nuclear plants.
Let me give this one to Mike.
Yeah,
how about
thanks. Yeah, that's an interesting point that nuclear plants is pointed out there, because the Department of Energy is currently investing in that area separately. I think that it'll be likely in automation or factory workers, where automation is currently being used in factories where you have to develop lots and lots of the same product. But products that we try to develop within the US or outsource as close as possible are the products where we're only developing maybe 1,000 of them. So can we develop only 1,000 products with a completely automated system? No. But if we allow that human intuition to work there, then we can bring this type of telepresence to systems where we're developing boutique or low quantity products.
Very good. Thank you, Mike. Well, that brings us to the end of this first Fast Pitch session. I'm sure there are many more questions out there or many more issues you'd like to discuss with us. Search us out if you want to talk more about these particular issues, and thanks again for attending.